Okay, this is lecture 15 on invariant maximality derivations by Harvey Friedman, please.
Thank you. Um, okay, so to orient ourselves, this is chapter 3 of the book in preparation. We started this after we finished chapter 4, and then chapter 4 was on the reversal. But here we have to prove the statements from large cardinals. So our book, the title is being fooled with all the time. Our book is, a second, I want to move this over. Uh, there we are. Here we are. Yeah. Okay. So our book, which I changed, I fool around a little bit with the title, is Invariant Maximality, Finite Free Choice, and Finite Games. And we're in the heart of invariant maximality, which is these sections 3 and 4. This section is the explicitly pi 0 1 forms. And this is some other finite forms that use games. All right. And the table of contents for this chapter is changed slightly, but we've been through this order. This basic section on order equivalence, the lead template for the entire subject, secondary templates, squares, roots, free sets, cliques, independent sets, uh, and uh, there's a lot of implications here. Basically, uh, the master one is the lead template from using order constraints, the lead template in here. And then these other ones are variants that are aimed at particular subject matters of mathematics. And these all follow from the general one with any order constraint. Usability means can you use it in the template? And we talked about two necessary conditions. Uh, uh, and we talked about usability in one dimension, which is completely analyzed. And then we talked about these statements are implicitly pi 0 1 and the falsibility notion, which is a notion that doesn't involve quantifier complexity like pi 0 1, but has the same effect. Falsifiability means that you know if it's false, then it's provably false. That pi 0 1 sentences have that property. Uh, and that property more or less is equivalent to, with some caveats, more or less equivalent to implicit pi 0 1. Usability is implicitly pi 0 1, and usability is stable under certain transformations. Uh, that's useful to have. All right, now today we're talking about finite usability. And I give a complete analysis of usability when the functions are finite. So the finite subject is completed. It's the infinite subject, of course, that is the more serious matter, and I start talking about that in lecture 16. And that leads to using large cardinals and necessarily needing large cardinals. So in the finite usability we're going to do, we have a number of sections. It's a bit complicated. So we're going to talk on 361 all the way through 367. And this entire development can be done uh, not in exponential function arithmetic, but in strong exponential function arithmetic, or super exponential function arithmetic, as I rather call it, meaning that this is based on the exponential function, and this weak system of arithmetic is based on the super exponential function. 2 to the super exponential n is a stack of n2s. Okay. This is for next lecture, all this. All right, so let's proceed with this. Okay. All right. So we want to characterize usability for finite f. And here is the theorem that we finally prove in section 366 after a lot of preparation. Uh, if I have a partial function on rationals from -1 to 1 that's finite, the following are equivalent. F is fully usable, meaning you can use it with the Lie template. F is too usable, meaning in dimension 2, you can use it with the Lie template. F is strictly increasing, and this is a technical condition, that's condition 3. F is strictly increasing, and we don't have F pushing 1 up and F pushing 1 back, meaning we don't have F pushing 1 up and F inverse pushing 1 back, so to speak. Yeah. And we also don't have the dual. We don't have the dual that F pushes 1 back and F inverse pushes 1 up. Yeah. All right, we don't have those inequalities. They both fail. All right, now it's obviously suffices to prove that 2 implies 1 implies 2, because 2 implies 1, 2 implies 3 implies 1, I'm sorry. Because 2 implies 3 implies 1 implies 2 is obvious, because 1 implies 2 is obvious, and we'd have a circle of implications. So we'd have the equivalence that we want. So it's enough to prove 2 arrows, 3 arrows, 1. Now, 2 arrows, 3 is by those theorems about necessary conditions for usability. 2 implies 3 is by the necessary conditions that we did earlier. And therefore, it suffices to prove that 3 implies 1. So the only thing missing is that 3 implies 1. Okay, and this is fairly involved. All right. Now, by the way, it should be remarked also, we should remark that 2 implies 3 was actually done. 2 implies 3 was actually done without the assumption that f is finite. Those implications work no matter what f is. However, 3 implies 1 depends on having f finite. We assume that f is finite for 3 implies 1. All right. We only have to worry about strictly increasing functions, I should add, because of the fact that we are assuming, basically we're assuming 3 and we want to get 1. Assuming 3 and we want to get 1. All right. So if you have a function f, it's strictly dominating if f of p is bigger than p for all p in the domain. And it's strictly regressive if f of p is less than p for any p in the domain. Then f restricted to e and f restricted to less than p, f restricted to less than or equal p, f restricted to greater than p, f restricted to greater or equal to p. These are all just ways of restricting the domain of f. All right. So in the first section, we take care of 2 cases. One is when the function has cardinality less than or equal to 1. That means it's either the empty function or just the constant function at one point, just a function at one point. The other case is just that f of -1 is -1, and I don't care about anything else, just as long as it's increasing, strictly increasing. All right. So we prove this alone as a standalone. And the idea is that if the cardinality of f is at most 1, well, if the cardinality of f is empty set, there's nothing to do. But if the cardinality of f is 1, then f invariance is extremely weak. It's very specific. And and it's easily handled by special observations. There's no issue involved that's substantial, but yeah, it's a little tricky to do this, but it's done in the manuscript pretty completely. Um, okay, if f is finite, strictly increasing, and f of -1 is -1, then f is fully usable. If f is finite, strictly increasing, and f of -1 is -1, then f is fully usable. Uh, the way this is done is not that's completely straightforward. The way this is done is you actually switch the context into the non-negative integers. Switch to the non-negative integers, and then you get um, a certain kind of indiscernible for a maximal solution to an order constraint. And using finite Ramsey theorem. And then there's a way of shifting the thing back into -1, 1 to get the result in there. You need f of -1 equals -1 to start properly. All right. Now, the real problem is when the real problem occurs with endpoints. So I proceed as follows. Suppose f is a star function. F is a star function if and only if it's finite, strictly increasing. F of -1 is greater than -1, and f of 1 is less than 1. F of -1 is greater than -1, and f of 1 less than 1 is, along with its dual, the real cases of interest here that have to be handled. See, if I had a f -1 here instead, that's false because I'm assuming that would contradict assumption 3, which is being used here. Assumption 3. All right. So f of -1 is greater than -1, and f of 1 is less than 1 is the definition of a star function. It has to be strictly increasing also. So I need some other notation. You say a number is less than a function if that number is less than everything in the field of that function. And a function is less than a number if and only if everything in the field is smaller than that number. And f is less than g if and only if given anything in the field of f and anything in the field of g, the former is smaller than the latter. That means that the entire function lives higher than the entire function g lives higher than the entire function f. Yeah. All right, so we need this decomposition lemma. Suppose f is a sharp function, then I can write f as f1 union f star union f2. So I can split the function into 3 pieces, where f1 is deterministically defined to go out as far as you can so that you're always strictly dominating. You go out from -1 as long as you can go, as far as you can go, so you're still strictly dominating. And the f2, the other function from the top, is you go least, you travel downward, you go least as long as you're strictly regressive. And this starts off strictly dominating because f of -1 is less than 1. This starts off strictly regressive because f of -1 is because f of -1 is smaller than -1. So you're starting off. Okay. All right. So this is all well defined. And now I've already defined what F1 and F3 are. I'm sorry. I've already defined what F1 and F2 are. So I know that F star should just be the residue, whatever is left. F minus F1 minus F2. Now, this construction has a few properties that should be important to talk about. Um, P1 is less than F of P1. Well, that comes from the strict domination. Is less than F of P2 is smaller than P2, and that's smaller or equal to 1. Okay. And then these are consequences. And then also P1 is the largest domain element of F1. And P2 is the smallest domain element of F2. And F1 of P1 is the max of the field of F1, and F2 of P2 is the min of the field of F2. All right. The domain of F is disjoint. So in between P1 and F of P1, and in between F of P2 and P2 is nothing in the domain of F. Nothing is in there. F1 is in the interval from -1 to F of P1 squared. And I guess that's clear from what I said earlier. And F2 is contained in F of P2 to 1 squared. Yeah. That comes from easily from this. All right. And I think this is also used. Okay. Now the domain of F is the same as the domain of F1 below P1. And the domain of F is the same as the domain of F2 above P2. All right. And then F1 is smaller than F sharp. F star is smaller than F1. And the F star is uniquely determined from the F. Now that's pretty clear because of this equation. Okay. All right. So now that we can decompose the function into these three parts, the first part is very so F has been written as F1 union F star union F2. So F1 is the so-called strictly dominating part. F3 is, I'm sorry, F2 is the strictly regressive part from the other end. And then F1 is going to be the residue, the function that hasn't been covered yet. Okay. All right. A star function is a strictly increasing, strictly dominating and finite, and defined at -1. So, for example, specifically in this decomposition, F equals F1 union F star union F2, we see that F1 is a star function, and actually F3 will be also it will be well, it's an anti-star function. It goes the other way. Yeah, but we're not going to worry about the other way until we do the forward way with strictly dominating. All right, so we need an extension theorem. We actually need two of them. This is one of them. We need an extension theorem that if you have a star function and a number below 1, then F extends to some star function G equals F union singleton PQ, Q less than 1. So yeah, so you can extend Of course, if P is equal to 1, you can't possibly extend because remember, it has to be strictly dominating. So you can't make it strictly dominating at 1 because 1 is the biggest number in the space. But if it's P is smaller than 1, you can do this. And you have to argue carefully about the shape of the function in order to actually do this completely rigorously. All right, if you here's the other one. Here's the other extension theorem. Uh, F extends if P is in the interval -1 and 1. F extends to a star function G equals F union QP. So we're taking the inverse of P. We're adding an inverse where Q is not in the field of F. We always want to be able to do this without using anything in the function right now, in the field right now, right? And we want where the field of F meets the interval QP. So we want a picture where we got some stuff here in the field and we're trying to invert this point that we go into this field, not necessarily all the way, but somewhat. For technical reasons, we want that. We want the field of F to meet the interval from Q to P. Um, let's see, I think if P is equal to 1, then we can't necessarily do this. I think that has to be an open interval, yeah, or half open. F is a closed function if and only if every P greater or equal to F of the -1 from the domain lies in the range. That means that we've actually added inverses to everybody, at least if it's greater than or equal to F of -1. All right, next topic. The orbits. The orbits of this function is the sets of the form Q, F of Q, dot, 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 F to the N of Q. And they have to be maximal. That means that Q cannot be inverted. That means that Q can't be inverted and that you can't go higher than, you can't apply F to FNQ. Now, obviously, the orbits of the function form a partition of its field. Yeah, because if you take any element of its field, it's got to have a value or have an inverse. If it has a value, there'll be a maximal thing, and so forth. Yeah, so that's not a problem. All right, now every star function extends to a closed star function. And this is done by successively adding new points. So, yeah, you can always add all the time new points to the function at any place it's not defined. It has to be new, add new inverses. So that way you will always get orbits. Yeah, let's see the definition of closed again. Yeah, closed means no, closed doesn't directly talk about orbits. It just means that everything in the domain lies in the range. Yeah, so you can get this also by these extension arguments. This here, every star function extends to a closed star function. Okay, now this one, suppose F is a closed function, then I can always take a closed function in any point in the range that's not in the domain. and extend it and still keep a closed function. All right, now there's a notion of regular star function. A regular star function is a star function where it's not only closed, but the orbits all have the same length. The orbits all have the same length, and the stuff that starts the orbits, i.e., the stuff in the domain that's in the interval, in this interval here, -1 to f of -1, that has cardinality R. And R is called a degree. You also want all the orbits to have length R. So all the orbits have length R, and all of the starting points of the orbits are at least R. Okay, and this is proved by induction. I mean, basically what happens is you take the star function and you start extending it. Um, and show that you are still a star function. In other words, you beef up everything to catch up with the number R. Okay. And every star function extends to a regular star function of any degree where it equals to the length of all of its orbits. Yeah. Okay. So we've sort of rounded things out. We took the star function, we closed it up by extending it. So we had all these orbits, but these orbits were all different sizes, and then we uniformed the lengths of the orbits. But then we have to uniform that also with the length of the starting point of orbits, which is in here. Um, that looks like a mistake here. Uh, that's what I meant to say. The set of starting points is R also. And then we want to claim that these are isomorphic. There's only one kind. This is only one thing like this. They're always isomorphic. This is a -1. Yeah. So any two of these are going to be isomorphic um, if the number is R for both. Next, now that we have these nice rounded out things here that are regular, uh, we want to extend to radial functions. Uh, but I think first we do the dual theory of what we just did. The dual theory being strictly regressive instead of strictly dominating. Okay, so this is just a repeat of the same thing except the dual. All right, now um, we say that f is a radial function if and only if f is strictly increasing, and for all p in the domain, f of minus p is minus f of p. This is an important notion. Radial if and only if f is strictly increasing, and for all p in the domain, f of minus p equals minus f of p. Now, from an earlier lecture, we defined the function minus of f as this. Minus of f at p is equal where defined to minus f of minus p. And so we get the easy fact that f is a radial function if and only if f is strictly increasing and f equals minus f. And so we get some basic material here about minuses. So f is an anti-star function if and only if minus f is a star function. F is a closed anti-star function if and only if minus f is a closed star function. F is a regular anti-star function if and only if minus f is a regular anti-star function, in which case f and minus f have the same degree. That's straightforward. Now, we have the same result for anti-star functions than we had before. They all extend to regular ones of any degree greater or equal to the length of all of its orbits and the cardinality of the start of these orbits. If f and g are regular anti-star functions of the same degree, then the functions, so to speak, are isomorphic. If f is a regular star function of degree r, and f and g is a regular anti-star function of degree r, so if you have regular and anti-regular, then these things are also isomorphic, but you switch signs. This is minus and this is greater than. Excuse me, this is less than and this is greater than. So there's this parallel subject of anti-star functions and anti and star functions and their extensions and so forth. Okay, now the main theorem. Let f be a star function. There exists g and a radial function h such that f is extended by g and g and h are isomorphic. In other words, let me put it this way. Every star function can be extended to a function isomorphic to a radial function. Every star function can be extended to a function isomorphic to a radial function. And this we proved by here. Okay. Now we want to show that radial functions are fully usable. Okay, so this is not completely straightforward to do. We have to come up with a notion of order equivalence that's much more lenient than normal. Okay, so x and y are order equivalent star if and only if there exists a k such that if you take the absolute values of the sequences, they're order equivalent. And also there's no sign change from the sequences have the same signs. Okay, so let's bear that in mind with a star equivalence. All right. Now this star equivalence allows us to get involved in invariance where we have positive and negative numbers. See, normally we don't have this two-sided stuff. So let E be contained in Z, K, R be order invariant and n greater or equal to 1. Then I can find a subset of Z minus T to T and integers, positive integers from 0 through T, such that S is maximal among the S, such that S to the R contained in E. In other words, S is a maximal solution to the constraint. And secondly, for all order equivalent star X and Y, they have to be order equivalent star, not necessarily order equivalent, right? Sorry, not necessarily. For all order equivalent star X, Y in plus or minus the A's, X is an S if and only if Y is an S. So we actually get a kind of invariance stronger than you might think, a kind of invariance here. All right, for a set. All right, now let F be a radial function. Then I claim that for every X in the domain of F, X and F of X are order equivalent star. That has to be done by a lot of cases. So if F is radial, then X and F of X are always order equivalent star. That's a paramount of bookkeeping. And now we can conclude that every radial function is fully usable because these two things fit together. You can easily get what you want from these two. All right. So now we're about to prove the main event, fin use. Which we stated before. Remember, the whole point is that we have to show that 3 implies 1. Okay, so we want to prove 3 implies 1 by bookkeeping. Okay, we already talked about that. Yeah. Okay, now if 3, we're assuming 3 holds for F. Let's assume that -1 is in the domain. Then we can extend to a radial function and get full usability. Also works dually if -1 is in the range of F. So there remains only the case where -1 is not in the field of F. So -1 is not in the field of F remains, but then we can extend F to be -1 at -1 and still be strictly increasing. And we already showed that such a function is fully usable at the beginning. Okay. So the point is that having both of these fail by careful bookkeeping, having both of these fail, meaning it essentially means that the function, unless that the function where -1 is in the field is covered by one of our processes for extending it to a radial function, which means it's fully usable. So it's already fully usable. We already know that if -1 or 1 is in the domain of F. Now, if neither one is in the domain, -1 is in the domain of F, or -1 is in the range of F, sorry. If neither one holds, then we get -1 is not in the field, and then we can do an ad hoc argument, that we did. Namely, we can extend the function so that its value at -1 is -1, and then invoke almost the very first statement of the talk today on this section. All right. Now, we still have to care a little bit about the computational complexity issues and EFA and SEFA. There's what we use to prove this. We discussed computational complexity considerations right after the proof of theorem 3321. We viewed elements of -1, 1 to the k as finite strings over the 5-letter alphabet. We then proved every order constraint on the S. We then proved, we proved that every order constraint on the S has an exponential time maximal solution, right? We did that with an inductive construction. But there's no invariance involved there, so we shouldn't get too excited about this. Uh, yeah. However, it's still true that here's the computational complexity form of it. Uh, Remember, it's three implies one. That's only the really important thing. And the idea is that you actually get full usability using exponential time invariant maximal set. In other words, you actually get exponential time there. That was the way it was done here. And the inductive construction is really the same as more or less the same as the one in here. So it's not surprising it's just going to be exponential time again. And that's what is the case. Uh, now, um, now let's talk about the provability because I just said exponential time. Recall that OC max X time is provable in EFA. Here we need to take more care, however, for the provability. First of all, we need to formalize fin use X time using a natural encoding of finite functions by finite strings in a finite alphabet and then integer codes. Now, some finite preparations are needed to set up these inductive constructions. I told you that the inductive constructions are used in a couple of places uh, in here. The constructions themselves with their complexity bounds are easily handled in EFA. And the finite preparations, yeah. First of all, we need to formalize this using natural coding. Now, some finite preparations are needed to set up these inductive constructions. The constructions themselves, with their complexity bounds, are easily handled within EFA. It's not a problem with the constructions, but the finite constructions are predominantly easily handled with the EFA as well. However, there are some places where there's finite preparations, we have to apply the finite Ramsey theorem. And we're applying the finite Ramsey theorem with arbitrary exponent, generally the exponent k, to achieve the finite preparation. And that uses CIFA, super exponential function arithmetic, and not just IFA. In other words, you need CIFA to prove finite Ramsey's theorem with indefinite, with free variable exponent. Okay? That's well known, actually, that it requires CIFA. So that's why CIFA comes in improving this stuff in section 6 as we just finished. Okay. All right, Andreas, I think I'm done now.